Welcome. We are in the module of reactor design and cost estimation. In the previous lectures, we saw some basic aspects of reactor design. We started with the basic reactor principles. Thereafter, we saw block diagram of the reactor procedure, reactor design procedure or algorithm. Thereafter, we tried to develop a simplified or general expressions for the reaction rate, material balance, energy balance, and then we got introduced about the economic evaluation of the reactor and the special constraints on reactor system. In this lecture, we take further this theme and then see the topics of reactor non-ideality, the residence time distribution, type of chemical reactions, and reactor types and catalysts. The reactor non-ideality, the first topic. The major cause of reactor non-ideality is the imperfect distribution of material and energy within the reactor due to transport limitation. This transport limitation can cause several undesired effects. First of all, the non-ideal contact between the species, the reduced reaction rate, increase in the undesired reactions, fouling of the reactor, kinetic variation due to temperature variation, then kinetic fluctuations can further be disastrous for, let us say, extremely exothermic or autocatalytic reactions. The temperature variation can lead to occurrence of unforeseen reactions, and which could not only cause the loss of reactant, or they could produce harmful side products and could also pose danger to the sustainable reactor operation. Then the mass and energy transport limitations could be of two types. Firstly, they could be on the molecular level or macroscopic level. The macroscopic level limitations could be due to the imperfection in the mechanical design of the reactor, which could lead to incomplete mixing and inadequate heat transport or heating or cooling. Now, these kind of non-idealities could be overcome to some extent or sometimes even completely by modifying the mechanical design of the reactor. The molecular level transport issues cannot be rectified by these kind of simple changes or improvements like the change in the mechanical design, because the scale on which they occur is extremely small. These type of transport issues can be encountered in fluid solid or liquid liquid immiscible systems, okay, like non-accessibility of the catalytic site of a catalyst, that is an example of molecular level transport issue, and some control over these problems can be achieved by changing, let us say, the morphology of the system, like for example changing the catalyst morphology, okay, which could make the catalytic sites more accessible, like for example increasing the pore volume, which could assist the transport of reactant molecule inside the catalyst and then the transport of the product molecule outside the catalyst. Then the next issue is about the residence time distribution. You have already had a detailed treatment of residence time distribution in the course on reaction engineering. So, here I give you only general background. Residence time distribution of reactants typically in a flow reactor is of paramount importance because it relates the reactor flow and its effect on non-ideality. Now, non-ideality, especially let us say for equilibrium limited systems, deviation from equilibrium or deviation from the theoretical conversion could be due to very low residence time in the reactor, in which the complete reaction does not occur. Now, these effects are more pronounced for slow reaction systems. The flow pattern in the reactor produces a distribution of particle residence time or fluid element residence time that results in the distribution of reactant conversion. Now, the flow pattern in the reactor is very important, whether it is a completely plug flow reactor or there is slight back mixing or complete back mixing. So, depending on this, the residence time distribution will vary. Determination of residence time distribution, this topic has also been covered in greater detail in the reaction engineering course. So, here I give only the basic information. It is usually performed using some tracer material or easily detectable inert tracer material. Tracer enter the reactor system in the same manner as the reactants and use the same flow rate and the carrier fluid. the tracer concentration at the inlet and exit of the reactor is monitored continuously, and the collected tracer response data is used to calculate the residence time distribution pattern in the reactor system. Now, is residence time distribution a perfect measure of estimating the reactant distribution in the reactor? No. There are some limitations, like for example, the duplication of tracer response. Tracer may not give a unique model of flow pattern within the reactor system, since several reactor arrangement may yield the same residence time distribution response. For example, if you have a series of CSTRs, that may produce the same RTD pattern as in case of a plug flow reactor. So, you should not use the residence time distribution data in its completely on its own. It has to be supported with some other measurement. Limitation on production of the unique flow pattern limits the use of tracer predicted RTD to simple first order reaction or with relatively constant kinetic constants. So, provided these conditions are satisfied, that your reaction is first order reaction and the kinetic constant is not going to change much with the concentration, temperature, etc., then in that case the RTD measurements could be a useful guide for design of reactor. How the non-ideality in the reactor could be emulated or simulated? Use of the ideal reactor model to emulate non-ideal reactor is both simple and useful. This methodology tries to fit an ideal reactor system to the actual reactor by examining of the result of the flow test in the design reactor, and thus the ideal reactor model are then arranged in combination to produce the same result as that of the non-ideal reactor, and thus the non-ideality could be accounted for to some extent. An example in this category is the biomass gasification, in which complete carbon conversion does not occur. So, what is usually done is that some restriction is put on the carbon conversion, and then the simulations are carried out assuming equilibrium conversion of other elements, and then the reactant species are estimated, and that gives the difference between the ideal producer gas that can be obtained by complete conversion of or 100% conversion of the carbon and the incomplete conversion of carbon. So, essentially what you are doing, you are putting restriction on only on the carbon conversion, not on the other elements like hydrogen, nitrogen, oxygen, and then you carry out the equilibrium calculation as if in an ideal reactor. So, these are some of the simple methods of estimating the non-ideality in a reactor. Now, let us see a major aspect of reactor design, that is the type of chemical reaction. Generalize the reactions or various types of chemical reactions, The first category is that of elementary reaction. For example, carbon plus oxygen giving CO2, or CO plus half oxygen giving CO2, or CH4 plus H2O giving CO plus 3H2, steam reforming of methane, so on and so forth. Okay. So, these are the simplest type of reactions in which the observed reaction kinetics matches overall with the reaction stoichiometry. Here the molecules of one or more species from react with molecules of another species to give molecules of third species, and the rate expressions in this case can be denoted by simple expressions as follows. Rate expression, you can use a very simple expression, rate with respect to A, that is reaction rate constant K, Ca, concentration of A raised to small a, which is the order with respect to A, Cb, concentration of B raised to small b, which is the order of with respect to reactant B, and then if you have n number of reactants, then Cn raised to n, where A, B, n are orders of reaction with respect to A, B, and the species that are involved. If it is a gas phase reaction, then you can also write the rate expression in terms of partial pressures, Pa, where is partial pressure of A raised to A. The order remains the same, however. Okay. Pa raised to A, Pb raised to B, and Pn raised to N. Okay. So these are the simplest type of reactions. We can write a generalized form of such reaction as A plus B plus N giving OO plus BP, like that. I can give you a very simple example of such another reaction. Say the reaction between chlorine and hydrogen gives ClO gas, and which further decomposes to Cl2 and O2. Two molecules of chlorine oxide can collide to give one molecule each of chlorine and oxygen. Okay. And in this case, the rate with respect to ClO minus RClO could be K C ClO squared, which could be 2 times the rate with respect to Cl2. Now, a major quantity here is the reaction order. There are 2 methods for estimating the reaction order. Or let us say quantification of reaction order. First is the overall order of reaction by summing up the order with respect to all reactants that are involved in the production of a particular product. Okay. Overall order of reaction by summing up of orders with respect to all reactants for a particular product. And the second is desegregation of order of reaction with respect to a particular species, and this is established from the species stoichiometric coefficient. Then the next reaction type is that of non-elementary reaction. Now, these reactions are characterized by the rates that do not match with their stoichiometry. Now, how do we go ahead with, how do we analyze the non-elementary type of reaction. It is often possible to represent non-elementary type reaction rate as a group of elementary reactions to simplify the analysis and provide qualitative design for non-elementary reactions. Now, example of non-elementary type of reaction is the gas phase formation of hydrogen bromide as established from Bodestein. Gas phase formation of HBr. The main reaction or the overall reaction is H2 plus Br2 giving 2 HBr. However, the reaction proceeds through several elementary reactions. First, bromine dissociates to give atomic bromine. Now, that we denote by superscript star. Br star reacts with hydrogen. Let us say with rest constant denoted by K1 to give HBr plus H star. This H star plus bromine further gives again HBr plus Br star, H star plus HBr give H2 plus Br star, then 2 atoms of bromine can combine to give bromine molecule, 2 atoms of hydrogen can combine to give 2 molecules of hydrogen. Now, if we assume that concentrations of atomic form of bromine and hydrogen remain constant throughout this process, then these reactions result in the following non-elementary type of reaction rate expression. The HBr, rate of formation of HBr, it can be K1 CBr star, concentration of bromine atom, into CH2 plus K2 into CH star plus CBr2 minus K3 CH star CHBr, which can be further arranged as K4 CH2 CBr2 raised to 1.5 divided by K2 CBr2 plus K3 into CHBr. How do we contrast the elementary and non-elementary type of reaction? In the elementary reaction type, there is only conservation of reactants, while in a non-elementary reaction type, we often see the reaction of reactants to form product and the reaction of product to form reactant back. Okay? So, that point to note. In elementary reaction type, there is only consumption of reactants to form product, but in a non-elementary type of reaction, both reactions of reactant to form product the reaction of products to form reactant back are seen. Then there is a category of reversible and irreversible reactions. In the module 2, the flowsheet synthesis, we have seen as how we can handle both type of reactions, taking HDA as a case study. In the hydrodealkylation process, the first or main reaction of toluene plus hydrogen giving methane plus benzene was irreversible type. However, the side reaction, that is 2 molecules of benzene combining to give 1 mole of diphenyl, was a reversible reaction, and we saw how we can shift the equilibrium to favorable side. Okay. Now, let us try to treat the same topic in a general way. Those reactions in which the reaction of reactants to form products is the only reaction are designated as irreversible reaction, and the reactions that involve both formation of product from reactant and simultaneous formation reactants from products are designated as reversible reaction. That point we note here. Reactions in which the reactants only react to form product are designated as irreversible reaction. And reactions in which both reactants react to form product and products react to form reactant back are reversible reactions. Then comes the category of catalytic reactions. Now, catalytic reactions could be classified on the basis of the phase of the catalyst that is used. If the phase of the catalyst is same as that of the reactants, then it is called as a homogeneous catalysis, and if the phase of the catalyst is not same or is different from the phase of the reactants, then it is called heterogeneous catalysis. For fluid phase reactions, usually solid catalysts are used because solids are convenient for contacting gases and liquids, okay, and they are easy to separate as well. Usually, the behavior of such catalyst is described by the Langmuir-Hinshelwood concept. Here, it is assumed that molecules of at least one of the reactant adsorb on the catalyst surface to react with another reactant, either gaseous or adsorbed, and then the reaction products are desorbed from the catalyst surface back to the gas phase. So, that point we note here. Okay. Catalytic reactions, 3 types as I just mentioned: homogeneous catalysis, heterogeneous, third is biological, but well, it can be put in the same category. So, we shall say the 2 categories instead of 3, homogeneous and heterogeneous. Then Langmuir-Hinshelwood concept, at least one of the reactants adsorbs on catalyst surface to react with other molecule to form product that desorbs from the surface. So, essentially the catalytic reactions have three steps. First, the migration of the reactant to the catalyst surface and adsorption, then the reaction between the adsorbed species, and then the disruption and back migration of the products. Now, if any of the three steps is slower than the others, okay, then it is called as rate limiting step or rate controlling step. The general form of the rate expression for such reaction is the kinetic term into the driving force divided by the adsorption term. This is the famous Langmuir-Hinchelwood, or which is also known as Langmuir-Hinchelwood, Haugen and Watson LHHW model for the catalytic reactions. Okay. Now, depending on various rate limiting step and the reaction order, the specific equations of the reactions vary. I now give you some typical expressions. The other expressions you can find from Perry's Chemical Engineering Handbook. Okay. So, that point we note, depending on the rate limiting step and reaction order, the specific kinetic expression varies. Now, let us see that what happens in case of surface reaction controlling or kinetically controlled reactions. In such cases, we denote the general expression for the reaction as A going to m plus n. The driving force for such reaction is obviously the partial pressure of A, but the adsorption term is 1 plus capital K A small p a plus capital K B plus small p b, the capital K m into small p m. Capital K m is the kinetic constant with respect to P, then capital K n divided by small p n, partial pressure of n. Okay, so, you substitute these here, driving force and adsorption term along with a kinetic term with some kinetic constant K 1 or something, and then you get the rate expression for that particular reaction. Okay. Now, if the same reaction is reversible, like represented as A going reversibly to m plus n, then the driving force is partial pressure of A minus the partial pressure of A into partial pressure of n divided by K, where K is a constant, and the adsorption term is 1 plus capital K A P A plus capital K M P M plus capital K N P N. So, this is as far as the surface reaction controlling mechanism is concerned, where the transport is sufficiently fast. Now, let us consider a situation in which the adsorption rate controls. The same two type of reactions. First, the irreversible reaction A going to m plus n. Now, in this case, the driving force is equal to partial pressure of A, P A, and the adsorption factor is 1 plus Ka by capital K into Pm into Pn plus Km into Pm. If it is a reversible reaction, A going reversibly to M plus N, then the driving force is still Pa, but now with a correction minus Pm by Pn Pa minus Pm into Pn divided by capital K, where capital K is the equilibrium constant, and then the adsorption term is equal to 1 plus capital K A by K Pm into Pn plus Km Pm plus Kn Pn. Okay. So, this is about the catalytic reactions. Now, another major type of reactions are enzymatic reactions. These reactions involve a reactant and an enzyme that combine reversibly to form a complex. The reactant portion of the complex is quickly transformed to product, and the complex then splits into the product and the enzyme which is released, and now this released enzyme from the complex can go further complexation again with another substrate. Now, this general equation we can write in a very simple way. I will just tell you. First, we note the points. Enzymatic reaction, a reactant and enzyme undergo a reversible process to form a complex, and the reactant portion of the complex breaks down to form product, and enzyme is regenerated. So, we can write the general expression for this. Reactant plus enzyme gives complex which further splits to products plus enzyme. The rate in such case can be typically written as R product is equal to small k e into central the total enzyme concentration. Enzyme is regenerated in the, so enzyme is a catalyst, so we have to consider the total enzyme concentration. Of course, total enzyme may not exist in free form because some enzyme will always be coupled to the substrate, but we take into consideration the total enzyme concentration in this particular analysis. Then the concentration of reactant or substrate you can call is equal to Kmm plus another Kmm is the constant and plus C reactant. This is a general form of the earlier expressions. Now, Kmm is called Michaelis and maintain constant. This is named after the scientist who invented this particular expression. Okay. Michaelis-Menten constant, not Michaels, I am sorry, I will change that spelling. Michaelis-Menten constant. Ke is the regular enzyme reaction rate constant. Now, the fourth category of reactions is that of biological reactions. Examples of this type are the traditional reactions such as fermentation of sugar to produce ethanol, okay, or fermentation to produce penicillin. These reactions most of the time are enzymatic reactions only, but carried out instead of using a free enzyme by using a microorganism, a biological species. Now, this species could be again in free form or immobilized form. Depending on the coherent sensitivity of microorganism, we have to design a process. The products of the enzymatic reactions inside a microorganism are secreted out, and they in some cases may adversely affect the growth rate itself. And a good example of this is the acetone butanol fermentation, where the product butanol itself tries to inhibit the reaction by harming the microorganism which are producing butanol. So, that is the a speciality of these kind of reactions. Okay. More, a microorganism may require a period of adjustment to the new environment, what is always known as the lag period, where they resume their regular cycle. Then the general expression, rate expression for biological reaction can be given as follows. That point we note, general rate expression, feed through organisms, microorganisms, go to product. So, the rate expression is KBO K is the kinetic constant, B standing for biological, BO standing for biological, 1 minus C SEC I divided by C SEC H star raised to N into C feed I into C BO I divided by C feed I plus C M. Now, I will list all the notations in this expression. KBO, as I said, is a reaction rate constant. CSECI is the concentration of secreted or product species, ith product species. Then C feed I is the concentration of feed species. C capital M is the monod coefficient. In some colleges, the biochemical engineering course is given as a separate elective, where more of these particular expressions are treated for different types of fermentation reaction. Now, as you might know that Monod coefficient is essentially the concentration of the feed species where the growth rate of microorganism is 50% of its maximum value. So, that point we note here Monod coefficient is the value of feed species concentration when the growth rate is 50% of maximum value. So, that completes our discussion on the reaction types. Now, we shall see briefly various type of reactor and catalyst equipment. Many of the industrial reactions are catalytic reactions where the catalyst is used mostly in the form of solid pellets. The reactor could be a fluidized bed reactor, a moving bed reactor, a fixed bed reactor. Those things we are going to see in greater detail later in this topic, in this module. But before that, we just see what are the factors that determine the selection of the catalyst. One major factor is the reactant conversion achieved with the catalyst, and then the product distribution that the catalyst gives, at what conditions the reaction occur, that is also an important factor. Okay, so, all these factors we list. Selection of catalyst. Okay. This is a crucial step in process design. As it affects the reactor type, residence time requirements, provide greater selectivity, and finally, all of these affect the capital and operating cost. Now, catalyst selection is not as explicit as the other factors of process design. Catalyst selection is categorized as both art and science, and trial and error experimentation and scientific analysis is always needed to select the best catalyst. Such an analysis can also form guideline for selection of catalyst for any other process that the company may like to take over. What are the desired characteristics of a catalyst? First is chemical constituency. Okay. The one element or compound is the key species in the catalyst performance, and the catalyst also uses several other promoters. Okay. Like for example, platinum, palladium, ruthenium catalysts are used for hydrocarbon oxidation and hydrogenation. Zinc and zinc chloride are used for a chlorination of organic compounds. Zeolites, crystalline aluminosilicate are used for cracking of petroleum fraction. Okay. So, that point we note. The characteristics of catalyst, the chemical composition, what is the main element and supporting elements. Then second is the physical form of the catalyst, whether catalyst is solid, liquid, if it is solid, then what is the shape of that solid. Okay. Once we select the catalyst composition and the phase, the other factors such as catalyst concentration and support have to be established. Now, there are different kinds of support for the catalyst. Some are hydrophilic, some are hydrophobic, some polymer support like aluminosilicate support, so on and so forth. So, depending on the reaction type, reaction condition, we have to choose a proper support that will give sustainable operations for the catalyst. Now, remember that catalyst is an expensive part of the process, and replacement of catalyst is not so easy, it is also highly expensive. So, we need a catalyst which is sturdy, which can go on without any operational problem for at least 2-3 years. Okay. Many times the catalyst company agrees to buy back the catalyst and regenerate and give it back to you. So, if whenever you are choosing a catalyst whenever you have choice of different companies for catalyst of a particular reaction, try to look for this particular alternative, whether the company itself is going to buy the spent catalyst after certain time, 1 year, 2 year, and give you the regenerated catalyst. Then the third aspect is the physical structure of catalyst. Whether catalyst is a complete solid or is it a porous solid, the catalyst sites are located on the surface. In some cases, the catalyst sites are inside the pore. Okay. So, the physical structure of solid catalyst is very important, especially for gas phase reaction, because it can cause mass transfer limitation. Finally, we also like to have as large surface area as possible. Typically, the surface area is in the order of 100 meter square per gram. Such large areas are obtained by using solids that contain micro and mesopores. Typical catalyst supports are inert solids such as alumina, silica, aluminosilicate, and the active catalyst species is usually deposited on the surface of the support. Okay. The reactant transport to and product from the reaction site within catalyst can limit the effectiveness or the utilization of the catalyst. So, you have already dealt with the catalyst effectiveness factor in the module of chemical reaction engineering. What is the concentration of the reactant in the bulk and what is the concentration of the reactant in the catalyst pores? That ratio decides the effectiveness factor of the catalyst. The reaction rate constant and diffusion coefficient, their relative values also affect the utility of a particular catalyst. In case there is steric hindrance, such as the reactant molecules are larger than the pores, then you can increase the diffusion coefficient by changing the pore size of the catalyst. Of course, by increasing pore size, you reduce the area, but you make catalyst sites more accessible. Then finally, the stability of the catalyst is also important. That point we note, stability of catalyst. As I just mentioned, some reactions could be harsh, high temperature, high pressure. So, your catalyst support should be strong enough to bear all the thermal variations, pressure variation, various stress and strain that are imposed over the catalyst. Okay. So, there are two types of stabilities. One is the mechanical stability and another is chemical stability. Okay. The mechanical stability is what I just mentioned, that catalyst support should be strong enough. It should not sinter, the catalyst should not get fragmented because of thermal variation. And the second stability is the chemical stability, which is in presence of impurities and poisons. Usually the sulfur containing compounds such as H2S can strongly adsorb on the reaction site and block them. In many organic reactions, the catalyst particle is coated with elemental carbon deposits, which also reduce their activity. So, the ability to regenerate the activity of the catalyst is very important. Protection of the catalyst from exposure to poisons is extremely essential. You have to scrub the gas whenever you are using syngas. If it has H2S impurity, you have to scrub the gas to reduce the concentration of H2S to ppm or sometimes even ppb level. The catalyst support must also have sufficient mechanical strength, as I just mentioned, and then it should sustain extreme operating condition or abnormal operating condition. Even if, let us say, some temperature surge occurs in the reactor because of heat transfer limitation, the catalyst should not get deactivated or fragmented. So, the mechanical stability is also an important aspect. So, that is how we have covered the various topics in this particular lecture. In the next lecture, we shall see the type of reactor and then the reactor design procedure, then the reactor cost estimation, and finally, we shall have a problem of reactor design.